In this video, we will take a look at Hamiltonian paths and circuits. Our new definitions are as follows. A Hamiltonian circuit is a circuit that visits every vertex once with no repeats. And of course, since it's a circuit, we have to start and end at the same place. A Hamiltonian path, like it, will visit every vertex once without repeat, but you don't necessarily have to start and end at the same vertex. We're going to contrast that briefly with what we've already looked at in the previous module, which were Euler paths and Euler circuits. Those are ones that traveled through every edge without repeat, rather than what we're looking at in this video, which is every vertex without repeat. So here is a couple graphs just to see this contrast. Now, on the left, we have a pretty simple graph with 4 vertices, A, B, C, D. If we started at A, notice we could just travel around like a baseball path, and we could hit every edge. And since we hit every edge and started and stopped at the same spot, that was, in fact, that circuit was A, B, C, D, and then back to A, then that would make that an Euler circuit. But notice we also traveled through every single one of the dots, every single vertice. So every vertex traveled through makes this, our new definition, a Hamiltonian or Hamilton circuit. All right, let's take a look at the graph on the right. Now, you can follow the same path, A, B, C, D, and hit every vertex. So that graph on the right also has a Hamiltonian because we went through every vertex. So it's a Hamilton. But there is no way, and we could try, but if you remember the previous module, you will find out that you cannot travel through every edge without repeat. I mean, you could try if we start at A, maybe we'll try going up to A and then maybe down through D and then over here and then over here and then back to D. Notice we get stuck. We haven't traveled through one of the edges, and I would have to repeat to go back and do that. So if you remember the previous video, remember if there's any vertex with a degree that's odd, in fact, all of these are odd, then there is no Euler circuit. So there's no way to travel through every edge without repeat. But in this, so what you find out is that Hamilton circuits are easier to find than an Euler circuit. And they have a different purpose. And so we're going to look at that purpose throughout this module. So let's look a little bit further on and see that it's not always as easy as it seems to find Hamiltonian path or circuit. We'll look at a couple examples. Number one, find a Hamilton path that starts at A and ends at B. Now, you'll have to play with this a little bit. You may pause the video and try it yourself before I do it. So we're going to start over here at A, and we have to end at B. Notice it's a path, so I don't have to start and stop at the same spot. Now, if you just kind of go at it and hope that you get it, if you just kind of tackle this, you might find that, oops, the only place I can go next is B, but I haven't yet went through every vertex. So you do have to do a little bit of planning on these. And so here's one possible solution. If you go start at A and go down to F and then over to E and then over to D, back up to C, and then down to H, over to I, J, G, and then B, that is an answer to a Hamiltonian path. Now you could write that out in letters, right? That would be A, F, E, D, C, H, I, J, G, and then back to B. That would be the Hamiltonian path. Now, we did not cover every edge. That's in the previous module. That's an Euler thing, right? Hamiltonian path or Hamilton path, we only need to go to every vertex. We did that, so we're done. Let's also find a Hamilton path that starts at F and ends at I. So let me go ahead and erase this so we can do that. So it's possible sometimes to go through the exact same path and answer a question, but I don't know that we'll be able to do that. So we're going to start at F this time, and we're going to end up at I. So I'm just going to take what seems to be a direct F, E, D, and then up to C then, okay, and down to H. And then we can go over to G, and then up to B, A, J, and then I. So I did it. I started at F and ended at I. I'm not going to write that one out, but notice that is also a path, not a circuit. Now, our last question says to find 2 different Hamiltonian circuits. So I wonder if there's a way, well, in fact, there is a way to travel to every vertex. But remember, if it's a circuit, we have to start and end at the same vertex, right? Same vertex. So there is a way to do that. And the trick will be to find 2 different ones. So let's start by just highlighting one that exists. It's going to look pretty similar to what we did before. In fact, we we can just copy this top one and then just go back to A. So let's do it. A, F, E, D, C, H, I, J, G, B, and then back to A. And you might think, well, is that a repeat? No, it doesn't count since we started and stopped at the same place. That would be a Hamiltonian circuit, all right? And then, so I can just basically take that and just write down the same thing. And all I would do differently is just add the letter A back again, right? Like I started and stopped at the same place. Okay, there we go. Now, I'm going to say something here that will be evident later, that if when you're finding different Hamiltonian circuits, it becomes very important to highlight them or to draw them out. Okay, I'm going to purposefully do that so that you can see that sometimes it is possible to accidentally find the same Hamiltonian circuit. So let's show you what I mean. So on that one, I started at A. Maybe I want to do something different. I say, okay, I'm going to go start over at C and see what happens. Maybe I'll go from C and then I'll go to H, I, J, G, B, A, F, E, D, and then back to C. Oh, look, I found another Hamiltonian circuit. Well, you may recall, and you can always go back in this video, that that's exactly the same drawing I had before. And here's why. If you start at C, notice I'll just right here in this middle where I wrote that. If you look at C, as your starting spot, notice that if you read the letters in order, C, H, I, J, G, B, A, and A kind of like, almost like Pac-Man, like it comes back to here, then F, E, D, and back to C is exactly the same circuit. So that's not unique. So it has to be unique if not just the letters are in different order. So let me highlight what I mean. This one is the same as, it's the same as the circuit C, H, I, J, G, B, A, F, E, D, C. It looks different, but if you look at the letters, they're in exactly the same order. So that is not different. Okay, let me be clear. I'm trying to find two different ones, all right? So we're going to go back and try it again. I need to basically draw a circuit that doesn't have exactly the same shape. And it is possible. We can even actually start at the same place. We can start at A, right? So F, E, D, C, and then go over to B, G, H, I. And you can see that that has a slightly different shape. That would be a new circuit, and we could write that one out. So pause for a moment, make sure you understand that. All right, so the key is that you have a different shape to have a different circuit. And we'll really illustrate that in this particular example right here. This one says, list all Hamilton circuits that start at vertex A. Now, it seems a little overwhelming, and it is a little overwhelming at first to tackle a problem like this. So that's why I'm doing it with you. And you can pause the video and try it yourself. You might find how many different Hamilton circuits start at vertex A. Okay, if you tried that, let's tackle it now. So one way to do it systematically is to start at A and then just go to whatever vertex you can connect to, and then just look at the possible path. So I'm going to show you kind of like what I mean by down below here. So if I start at A, maybe I think first, okay, well, I could go to C. If I went to C first, what could I do after that? Well, it looks like I can either go to F or B, right? So I can go to F, that's one possibility. Or, and I'll draw this on the next graph, I could have gone to B. Those are two different possibilities. Now, it turns out that once I make that second move, there's only one possible way to get to the ending place. So let's start with the first one where I'm at F, okay? If I'm going to get back to A without repeat, I cannot next go to E, because then I would be stuck. I'll show you. If I go over to E, that won't work because I can't get to D and B both. They're two opposite directions and get back to A. So that means there's only really one possible way to get around after this, is that I have to go to D next, and then E, and then B, and then back to A. That's every vertex. However, if I went to B, the only possible way to get back to A is E, and then F, and D, and back to A. So those are two different circuits. You can notice that they're different shapes or different paths, right? They're not the same part of the diagram. So that's what could happen if you started at A and went to C. But what if you didn't go to C? What if you went maybe to D? Okay. If you went to D, it looks like after D, there's two options, either F or E. So I'll try going to F. And then I have another copy of this down here, or I'll try going to E. Let's see what happens, the difference between those. Well, if I went to F, I would definitely have to go next to C, it seems like, right? Because if I went around to B and to E, oh, actually, I did that backwards, right? Actually, I'm stuck. So I made a mistake there. Well, that's okay. It happens in these. All right. So if I went to F, I can't go to C. I just noticed that. I would have to go to E, and then B, and then C, and then back to A. All right. That looks good. Now, one thing you might notice is that these two are equal. oh, I didn't find a unique. These two next to each other are exactly the same shape, right? That's not unique. So that one doesn't really count. Okay, let's try the next one though, down below. What if I went ADE? Well, then I could, to get back to A, I'd have to go over to F, C, B, and then back to A. That looks to be a new graph that I don't have yet. All right, so that's what happens if I go from A to D. The last thing to consider is if I started at A but actually went to B, right? I'll try that. There's actually two different ones. All right, so if I went to B, one route is to go to E first, all right? And then I would have to go D, F, C, and back to A. The other option is if I didn't go to E first, if I went to C first, and then I'd have to go F, E, D, A. Now, if you look in total at these pictures, you'll notice that the very first one I did, right? This one, I'll just kind of like put shading in it. Like that one right there is the same as that one. It's the same picture, right? And then let me use a different color. This graph is the same as this graph. You can see it's exactly the same outline. And then this graph is actually the same as this graph. They look kind of like identical tracings. So that means there's actually only 3 different circuits. There's only 3 different ones. All right. And what are they? Well, you can name those in different ways. But if they start at A, and which is what it asks us to do, we should definitely list that first. So I'll just take a look at this first one right here, which is the same as that one. All right. That one is one where we started at A. And you can, and I remember that the first one I listed as going to C, but this last one I was talking about going to B, but it turns out it's the same either way. Let's show you what I mean. If I go to C first, it would be A, C, F, D, E, B, A. Now, if you look at this graph down here, it's actually just in reverse, A, B, E, D, F, C, A, which means that you basically just read this circuit backwards, right? So you can read them from left to right or right to left, and it's identical. Kind of cool. Okay, the second one would be either one of these two right here, all right? That would be if I started at A and then went to C and then B and then E and then F, D, A, or again, you can read that backwards. And then the last one was in either one of those bottom left or bottom right. I'll just use the bottom left. That was with A, and then I went to D, E, F, C, B, A, or I can read it backwards and I would end up the same as that. So there's only 3 different ones. And so question 2 says, why would there be the same number of circuits no matter which vertex you start at? That's kind of an interesting question because the reason that we did this is to give us an idea that if you don't have a starting spot, it's really hard to have a system. But it turns out if you wouldn't have used vertex A, if I would have asked you the same question from vertex B, C, D, E, or F, you would have the same exact 3 answers because these are the only paths, or excuse me, circuits that are possible. You can't draw a different circuit. And so there would be no different answers. You would basically just be starting at a different spot. Like if I'd ask you to start at C, for example, the letter C, look at right here. One possible answer would be C, B, A, D, E, F, C. Like you can just read that in order, almost like, remember like the game of Pac-Man, right? I'm just gonna, oh, that's a really bad Pac-Man. Let's try that again. There's your Pac-Man. If you're going off the screen, right, this way, you kind of just come back on the screen that way. That's how you can kind of read these. Okay, time to practice. Okay, now that you've practiced, I hope that you've learned more about Hamiltonian circuits from this video and Hamiltonian paths.